Okay. So hi everyone, my name is Olivia Clifton, and I'm very pleased to introduce Dr. Maria Molina today. She's an assistant professor in the Department of Atmospheric and Oceanic Science at the University of Maryland, College Park. Her research group focuses on climate and extremes data science. And prior to arriving at University of Maryland, very recently, I think, Dr. Molina was a project scientist in the Climate and Global Dynamics Lab at NCAR and an ASP postdoc fellow at NCAR, where we were peers. Dr. Molina received her PhD from Central Michigan University in 2019, and as perhaps our GISS and Columbia audience would like to know, received her master's in the Climate and Society program from Columbia in 2015. So with that, Maria, I'll ask you to take it away.
Awesome. Thank you so much for the invitation to be here, and thank you for that wonderful introduction, Olivia. It's really nice to be here with you all today, or at least virtually. And I'm excited to share some recent research with you all, some of which is based on the physical sciences and some of which is based on some societal concerns. And I have my pup here with me in the office at the University of Maryland. And of course, she just decided that she wanted to join me on this chair right as I was starting the seminar. Perfect timing. But I'll be talking about machine learning-based predictability assessments using unsupervised learning and also bias correction of subseasonal precipitation. And that approach will actually use a supervised learning framework. But I want to start off a bit more broadly to kick us off, where we can think about all the different places and ways that we can use machine learning when we're thinking about Earth system modeling, and specifically thinking about these mathematical numerical systems that we have built over many decades that can be initialized with some initial state of the atmosphere, ocean, etc., and can be run forward in time to some predefined lead time that we are interested in, right? And so if we think about this Earth system modeling workflow, we can actually separate these steps into three overarching categories, right? So we can think about initializing a numerical model with the input stage, then there's a running the model stage, and then there's the output stage where we can analyze some of the predictions that were generated by that numerical system. And we can actually use machine learning across any of these different stages in that numerical modeling framework. So before we even begin running a mathematical model forward in time, we can actually use machine learning methods to perform observation quality control, so to improve that initial state and representation of the system that we're going to be modeling. And there was a paper published a couple of years ago now, led by a graduate student who has since graduated and was visiting NCAR for a summer and ended up using a deep learning approach to quality control observations of precipitation and temperature over portions of the Western United States. And this paper specifically just focused on precipitation observation quality control, but he also did some work with temperature out west. And then we can think about using machine learning as the numerical model is running forward in time. So the motivation there might be to either improve some physical process representation, perhaps at the subgrid scale. If we have a coarse model that doesn't explicitly model convection, we can think about using parameterizations that we often use and training a machine learning model to perhaps improve the representation of that process. But we can also use machine learning to reduce the cost of high performance computing and allow us to actually accelerate the computation of our numerical modeling, which can entail many different components. But the advantage there is that we can perhaps generate more simulations and have more ensemble members to try to quantify confidence in a certain outcome. In a recent paper that was published, led by Andrew Gettleman out at NCAR, entailed using machine learning to generate a machine learning model that would emulate the warm rain process. So really thinking about clouds at the subgrid scale, and then trying to put that back into a numerical model that would run forward in time with that machine learning piece embedded. And then we can think about, once we have finished running the numerical model and we reach the output stage, we can actually still use machine learning to either improve our predictions, so do some bias correction after the fact. We can detect features within our numerical model output. For example, detecting tropical cyclones or atmospheric rivers. And then we can also use machine learning to extract knowledge from all of this output that we have from our numerical models, which is up onto the order of petabytes now when we're thinking about like CMIP class models and lots of Ensemble members. And so here I have an example of a paper during my postdoc actually where I extracted these thunderstorm objects from a high resolution convection permitting simulation generated with WRF on a climate scale or climate time scale. And then went ahead and classified these thunderstorms based on their likelihood to produce severe hazards like tornadoes and large hail. So again, we can use machine learning to extract knowledge or to improve whatever task we are interested in once we're done running the numerical model. And so today I'll be focusing on the topic of subseasonal forecasts. Many of you perhaps are familiar with this topic, and if not, that's totally okay. This was actually relatively new to me just a couple of years ago. And so subseasonal forecasting is just this idea that we have some mathematical model. This could be, initialized using a numerical modeling framework or any different type of model. In this case, I'm going to be focusing on the CESM community Earth system model, so a global coupled model that we'll be running forward in time. But really the idea is quite simple, right? We have some initial state, and then we go ahead and initialize that model using some initial conditions and run it forward in time out to some time frame of interest. At the subseasonal time scale, that means 2 weeks out into the future or even up to 2 months. So really, again, below the seasonal time scale and at least several weeks out from initial time. And so the issue with subseasonal forecasting is that it is actually very difficult. This time scale has numerous challenges. And so usually we see a model state that has drifted away from what actually happened. So some observations that we would know after the fact if we're predicting some time into the future. And the reason for this has numerous sources, right? So we actually can have errors that arise from the model itself. So we know that we have parameterizations, these representations of processes at the subgrid scale that are just impossible to explicitly model at that very, very small scale. And so we have some estimates that we use to try to approximate what's going on at the subgrid scale. So that is one source of error. Models themselves have their own biases, and this is also a contribution to error. We also have computational errors, meaning even if you had a perfect representation of the Earth system, you're still going to be approximating decimal places, for example, in a numerical model that you're running on a computer, and that's going to be one source of error, so truncation. We're also approximating a grid. We're using a grid to approximate processes occurring across the globe, so that's going to be another contribution of error. And then, of course, simply the fact that we're trying to predict out to a lead time of 2 weeks or more, where we don't have many sources of predictability. So from the physical system itself, we tend to get predictability at short lead times, so about 1 week from the atmosphere. Meaning if I initialize a numerical model and run it forward in time for about 7 to 10 days, much of the predictability comes from the atmosphere itself. But then into longer time scales, so at the seasonal time scale, about 3 months or so, predictability arises from slower evolving processes and systems such as the ocean or the land. But at that subseasonal time scale, that's about 2 weeks to less than 3 months, we're at a predictability desert. And so that is another challenge for us. And then, of course, on the left-hand side, you see a box that's called initial condition errors, and that stems from the fact that it's really just impossible to perfectly model or represent the Earth system at that initial state. We just simply don't have observations at every single point on Earth. And so one of the ways that we estimate that initial condition error or try to account for some of that uncertainty is by initializing multiple simulations, right? So we may perhaps perturb the initial conditions a little bit, so modify the temperatures just a bit and run the model forward in time. And we can do this iteratively several times and end up with an ensemble that gives us some approximation of uncertainty over time. For example, if I start at this state and I go forward in time, what would be my outcome? And if I am a little bit different, what would be the outcome then? And so this gives us a distribution of uncertainty from our initial conditions. And then we can also get a distribution later in time, which is usually greater than it is at the initial time because we have uncertainty and spread in the possible outcomes from that initial state. And so again, this is really challenging to do. And if we consider skill for different variables, and so here I am showing you skill for the community Earth system model. We have different versions and configurations, but really the most important thing to know is just that we're comparing skill for temperature on the left-hand side and precipitation on the right-hand side, only over land points, and this is globally. This is from a paper that came out in 2022, just documenting the subseasonal community Earth system model version 2 configuration. And so what we see is that as lead time increases for both temperature and precipitation, skill, of course, decreases. ACC is anomaly correlation coefficient, so closer to 1 means you're more close to what the observed state was. But then if you compare the bars on the left side and the right side, you see that in general, precipitation skill is much lower than temperature skill, right? And this makes sense because temperature is a much smoother field when we consider it on a global scale or even regionally, but precipitation is a quite noisy field and there's lots of processes physically that are very difficult to model at the subgrid scale as well, so that contributes further to the challenges with precipitation skill. But getting to predict temperature and precipitation is really important, and particularly when we're thinking about extremes. And we know that historically marginalized communities do experience disproportionate vulnerability to not only extreme events, but also to a changing climate. So this is a concern moving forward. And skillful subseasonal prediction could potentially allow decision makers to make more informed decisions about how to try to mitigate some of these issues that could be coming up based on a forecast. And so again, on the right-hand side here, what we're looking at is those sources of predictability. As I mentioned, the atmosphere provides skill during shorter lead times. The ocean provides more skill during later lead times, and we get some predictability from the land. So thinking about soil moisture and other processes or variables that could help us out at the subseasonal timescale. But in general, it is quite difficult. So what we decided to do was to simplify the forecasting problem. Instead of following the same framework that is usually followed, where we assess skill based on a global grid of temperature or precipitation anomalies, we decided to instead forecast on large-scale patterns, so weather regimes. And so on the left-hand side, you're seeing a representation of what weather regimes typically look like. These are geopotential height anomalies across the northern hemisphere, and you have areas of positive and negative anomalies representing, for example, high and low pressure systems, respectively. And so for this project, we ended up using unsupervised learning, and the supervised learning approach entails a convolutional neural network, which I'll be detailing at the end of this talk. But first, focusing on the weather regime concept. So the idea here being that we can hopefully make the forecasting problem a little bit easier on the subseasonal timescales by thinking about what these geopotential height anomalies will look like at large scales, right? So if we have positive anomalies, we're thinking about more persistent high pressure, negative anomalies, more persistent low pressure. And these weather regimes do have a signal that they imprint on the surface. So here we have the precipitation anomalies at weeks 3 and 4 that are associated with one of our weather regimes. This is the Alaskan Ridge, and we can see that generally where you have high pressure anomalies, you see at times negative anomalies or drier conditions, but in other times you can actually have some positive precipitation anomalies. So again, this is just anomalies in the large scale flow. And so the way that we did this here for this project was we actually took a reanalysis product, so ERA 5, geopotential height anomalies, and used that reanalysis data to train k-means clustering, and then applied that k-means clustering algorithm that was trained with reanalysis onto CESM, so that we can actually assess whether the prediction system is representing the climatology of these weather regimes skillfully. We have about a 20-year period of reforecast with the CESM2 modeling system. And so that's really what we're looking at here. So again, we have 20 years of data for CESM2, and we have the corresponding ERA 5 reanalysis data. So what we're seeing here is, again, I trained k-means clustering using ERA 5 data, and then applied those same centroids and extracted the corresponding CESM2 weather regimes. And what we can do when we follow this sort of method is we can look at how they correspond across lead times. So at day 0, we're comparing ERA 5 and CESM2, and we see that overall, the frequency of occurrence for weather regimes align very well. So this is good. So we're not seeing much bias at early lead times with CESM2. But what starts to happen during later lead times, so especially once you get to weeks 5 and 6, we start to see biases emerging with CESM2. So suddenly a overoccurrence of the West Coast high regime takes place. So that means that this initialized prediction system, CESM2, is generating too many West Coast high regimes at later lead times. And then we can also see that the Greenland high and Alaskan ridge regimes are less represented. Overall, this is still pretty good performance, but nonetheless, there is a bias here that we're seeing emerge, and it seems to be like a systematic issue. And this is a way to use an unsupervised learning method, very simple k-means clustering, to extract these signals from an initialized prediction system. And so this can be done with any model to assess its representation skill with these weather regimes. And something else that this k-means clustering or any unsupervised learning approach allows us the opportunity to do is that we can also assess ensemble member spread. So CESM2 initialized prediction system at the subseasonal timescale has 11 ensemble members. Here I only have 5 lines in the schematic, but the idea being here that we can actually use that k-means clustering separation of weather regimes to track how weather regimes evolve over time along these trajectories. And when we do that with all of our ensemble members, we actually saw this really interesting signal emerge where, while in general, most of the times, most initialized predictions did generally increase in spread, again, as you increase lead time, there were some cases where ensemble member spread increased and then decreased during later lead times. And so we thought that was a really odd thing. I went through the code. I was at first worried that I just made a bug in my code, then talked with collaborators and so on. And so one of my collaborators said, okay, well, let's say this is real, right? So everything is fine in your code. This could just happen by chance some of the times, right? Because you only have 4 weather regimes. And so what is a big deal? This maybe just happens by chance some of the time. And so I said, that's a good point. And so what we did was we took these example cases where this thing that I'm calling ensemble realignment occurs and looked at the upstream patterns. And I will say, I don't think I mentioned at the start of the talk that if you have any clarification questions, I'm totally happy to take those. And I imagine that this plot is pretty confusing, so please feel free to interrupt me at any time. But what these plots are showing here is one of the initialized forecasts, just as an example. So this was a forecast initialized on November 9th, 2015. And what we have, again, 11 ensemble members. And what we're trying to visualize here is how much ensemble members were agreeing. And as you go forward in time, you start to see ensemble member agreement decreasing, which makes sense. But then suddenly here's this increase in ensemble member agreement. So there's like higher confidence in this specific forecast. And then it again decreases. And so it was a question as far as like, well, why does ensemble member agreement increase? In other words, why does ensemble member spread decrease? And how come it got this right at this case? So ERA 5 and CESM were both suggesting that it was a Pacific trough regime. And so we went ahead and looked at some fields upstream of North America to see if there was any signal that we could uncover. And it turns out that when we look at outgoing long wave radiation, just over the North Pacific, just upstream of North America, we also see a corresponding increase in outgoing long wave radiation representation. So you can look at other spatial fields, and essentially what we're seeing is some sort of Madden-Julian oscillation signal or convection over the tropics propagating across the North Pacific and helping to align these ensemble members and also generate reduced spread. So that was kind of interesting there. So there are times where this is physically driven or can be at least explained due to some upstream patterns of North America. And so with that, I will give a caveat that the ensemble realignments do at sometimes actually result in reduced skill, meaning sometimes the ensemble members can agree quite highly and realign, but be wrong. So it's not like they're always correct when this happens. So that's just something to note. And so I'll go ahead and move forward and give a quick overview of 2 additional projects that we're currently working on with machine learning on the S2S timescale. And so here what we're thinking about is using machine learning in 2 different directions. So we can think about using machine learning and applying it to some initial conditions, and then using machine learning to predict forward in time, right? So we could start at lead time 0, use machine learning to predict into the future. Or we can use our week 3 or 4 predictions from our numerical modeling system, and then use machine learning to bias correct at that same lead time, whatever our forecast is, and hopefully yield improved skill. So again, these 2 different directions that we can apply machine learning for a very similar problem. And so I'll give an example for this first one, this diagonal example of going from observations forward in time. So right now, I actually have a PhD student in my group named Jairon, Steven Perez Garasquilla from Colombia, who is quite bright and has already trained a convolutional neural network to predict these weather regimes into the future. And what he has done is he's taken different components of the Earth system and grabbed variables from them. So for example, geopotential height at 500 hectopascal, outgoing long wave radiation, or then you can also think about the ocean and land. And using these different variables and training a convolutional neural network, he's able to actually extract predictability signals, meaning we can see that the atmosphere provides predictability a lot during earlier lead times, whereas other components of the Earth system perhaps provide more predictability later on. And in general, the convolutional neural network is able to beat persistence, which for weather regimes is quite difficult because by definition, weather regimes are persistent. And so I'll give you another very quick example of thinking about using machine learning from a bias correction standpoint. So in this case, we ended up using global products that have observations globally. So here we're looking at the NOAA GPCP product, where we have precipitation anomalies, and we can also use a reanalysis product. Although it's not exactly observations, we're still modeling this to generate this grid, but nonetheless, it's at least closer to our representation of what actually happened. And now that we have data everywhere, we can actually go ahead and do this bias correction. There are numerous models that can be used for this sort of problem, but what we ended up finding was that a UNet type approach, where we have an input image and we generate an output image, was a really helpful use of or a very helpful architecture to use for this problem. So what we ended up doing was we took CESM2 fields, used that as input, and then we showed this neural network observations, right? So the corresponding observations that actually happened. And in many cases, there were some systematic errors that could either be related to mountain ranges or other like coastal regions, or maybe it was an area that didn't really have much like land. It was a more oceanic region. Those are important details that the neural network is actually able to encode and generate and use to generate improved predictions. So overall, what we're finding so far, this is still ongoing work, is that if we use regions, so here we have a 20 by 20 grid cell image across the central United States and in the Great Plains. If we use these smaller regions and train it to learn what the actual observation was, this UNet architecture can actually yield quite a bit of improvement over what is being produced by CESM. So this is, again, ongoing work, and we're currently going to be working on scaling this approach to generate an ensemble of bias correction models. So again, 3 different approaches here for unsupervised learning, supervised learning, and then a combination thereof that Jairon, PhD student, is currently working on with that neural network-based prediction of weather regimes approach. And I went a little bit quickly because I do want to actually share something that's in a bit of a different direction. So bear with me. I want to give you some examples or share some recent work that focuses on science communication for marginalized communities, and also the representation of marginalized communities in STEM. And so this is a topic that's near and dear to me. As we briefly mentioned in one of these slides earlier, we know that historically marginalized groups are going to be disproportionately impacted in a changing climate, and we're already seeing this in extremes. This is a recent example from Texas back in February 2021. This was featured in Time magazine, but again, we have so many examples of these types, unfortunately, where we're seeing the disproportionate impacts from weather extremes. And so first, I'm going to share a project that was led by Anareli Morales. Anareli Morales is a former ASP postdoc that was actually in the same cohort as me and Olivia. And so Anareli led this project that focused on looking at culturally relevant science communication and how that could impact the retention of information and people's perception and trust in the information that is being shared. And so what was done was there was a video created that was more traditional style documentary format. And then there was a video that was generated using more of a conversational style communication. So this was a bit more of an informal approach where you had a pair of friends that were just having a discussion, and the topic of mountain weather came up because they were near the mountains having a picnic outdoors. And so the hypothesis was that perhaps conversational style videos would create more trust and would be much more, would trigger more engagement from participants that were viewing those types of videos, as opposed to traditional videos where we have an expert that is being interviewed and then concepts that are being explained. And the results that came from this survey were actually quite surprising. So I want you to first ignore the different color shadings here. What we're seeing here is just the preference of video style by Hispanic and Latinx participants in the survey. And what we're seeing here is that most participants, so over 50% of people that filled out the survey, actually preferred the traditional video style over the conversational video style, which was quite, again, surprising. And then, of course, you can further stratify this based on the language of choice by participants, right? Whether they primarily spoke Spanish at home or were bilingual, but nonetheless, the signal was quite surprising. And then there was anecdotal longer format responses that were provided by participants that actually shared the reasons why they preferred the traditional video style. And it turns out that the conversational video style for some participants felt that it was too informal and they didn't really trust the expert anymore when they were having just a conversation at a picnic. And so again, this is just one study. Of course, it could just mean that the specific videos didn't resonate with viewers, but nonetheless, it was quite surprising to see this result, right? That Hispanic and Latinx adults actually prefer the traditional video style instead of the conversational video style. Regardless of the preferred video style, the participants did report positive feelings associated with these two videos, and they really felt that the conversational style actually did have quite a few pros, right? They were able to retain a lot of the information that was shared in that conversational setting. So I guess long story short, probably both styles are needed, which is probably not the answer that anyone wants to hear because it's just more work on everyone. But lastly, I'll go ahead and share this last paper. This is a paper that really was motivated by a lot of us that were participating or are participants in the AMS Committee for Hispanic and Latinx Advancement, which we call CHALA. So we are a bunch of participants that basically are part of the academia sector group. You likely recognize this name, Susana Camargo, who is based at Lamont. And essentially the idea here was to add quantifiable evidence that there is a lack of representation in Hispanic and Latinx adults in the earth and atmospheric sciences. And you might say, well, duh, but as participants, we ourselves noted that we have experienced perhaps the dismissal of these statistics, or perhaps folks saying, this is again anecdotal, but perhaps folks telling us that things are getting better and improving and so on and so forth. And so we were like, well, why don't we go ahead and quantify and show with numbers that whether this is still a problem or not, or what exactly is going on. So what we were able to do was we took IPED's data. Unfortunately, I don't remember what IPED stands for, but I'm very happy to share that with you all later. But essentially, this is providing data from institutions of higher education. There are numerous institutions that are included in this data set, including two-year colleges, four-year institutions, and doctoral providing schools. And what we did was we went ahead and looked at different segments of the atmospheric sciences, the earth and atmospheric sciences, and also the physical sciences, right? In those different categories, the reasoning there is that not all universities offer a major that is just specifically atmospheric science. But here I'm going to just share with you earth and atmospheric sciences. The signal is pretty consistent, as you can imagine, across, no matter how you slice the data. So in general, when you're considering earth and atmospheric sciences and the top bachelor degree granting universities, and by top, I mean number of degree completions, you see pretty good diversity in terms of where these schools are located, right? We have schools across the southern US, the northeast US, and out west. It's pretty well distributed. But then when we look at the top Hispanic Latinx bachelor degree granting universities, specifically in earth and atmospheric science, suddenly a signal emerges, which is not perhaps surprising. Places like Miami, across Texas, California, and along the I-95 corridor, or this is likely Penn State, are schools where many Hispanic and Latinx degree folks are getting bachelor degrees in Earth and Atmospheric Science. And so I guess geographically, there is a very robust signal in where students are going to get degrees. But something that was perhaps a bit disappointing for a lot of us as we were looking through this data was we went ahead and considered bachelor's degrees versus master's degrees versus doctoral degrees. And again, looking at each of these different categories, physical science down to the more specific atmospheric science. And the percentages are quite low, especially when you get to the doctoral degree granting stage, right? I mean, in atmospheric sciences, the number, and this is just over the last decade, is only, it's less than 3% out of all doctoral degrees granted in atmospheric science. So again, we can see the signal very robustly in our data. And you might say, well, most of the population is not Hispanic and Latinx. Well, it turns out that approximately 1 out of every 6 person in the US is Hispanic and Latinx identifying. So that means that if we were to have this percentage actually be representative of the US population, this number should be much higher, right? So we should be looking at approximately, I don't know, like 18% or 16% or so to be representative of the US population. So this is not representative of our diversity. And so we are wondering whether this is improving over time. And so if we only consider the atmospheric sciences, unfortunately, the data is way too noisy because our sample size is so small. So here I'm sharing Earth and atmospheric sciences. And what we can see is that over time, at least at the bachelor's degree level, indeed, you do see a positive signal. The numbers are increasing and getting better. And this is also the case at the master's level and at the PhD level, although it is a lot noisier at the PhD level and a bit difficult to see any robust signal. But nonetheless, hopefully, this means that things are getting better. And of course, I'm only focusing on Hispanic and Latinx groups, but you can imagine that this sort of analysis could be done and likely has already been done for many different sectors of the population. And so with that, I will leave up these 2 papers, again, considering the topic of culturally relevant science communication and also, providing statistical evidence of things that I guess we talk about and have anecdotal knowledge. And I'll end by saying that something that we really emphasized in this paper was that at times there is a lack of data that can provide quantifiable evidence for things that people are feeling, and that we really should try to find a way to somehow represent this sort of anecdotal knowledge and lived experiences by humans in STEM and science, right? And not discount these experiences just because we can't represent them with numbers. And with that, I'll end. Thank you all so much for your attention and for the opportunity to share this.
Okay, I think we can open it up to questions for either or both parts of the presentation. Thank you so much, Maria. So if there are any questions in the room or online, if you just want to unmute yourself. Yeah, Letty.
I can ask a question. Thank you very much for the talk. On the second part, you showed that big drop-off in completion of doctoral degrees after masters. And I wondered if you have a sense from the data of whether that's, if there's people that begin those degrees and there's a big dropout during the degree, or it's not getting into those programs in the first place.
That is a great question. And so, yeah, and I think we noted that there are lots of things that we might have a hypothesis on, but we can't quantify, right? So the only numbers we're able to see from IPED's data includes degree completions. I believe there might be enrollment somewhere, but then things get really tricky in how they're stratified and all and so on. So we were only able to quantify degree completions when we were looking at this. So there is a gap in that data. And then another question we had that sort of related, which is, okay, we have this number of professionals that are getting their PhDs and completing the degree. Where do they go? And so we noted that there is no way to quantify postdocs easily, right? Not all people that complete PhDs go on to a academic setting to complete a postdoc. Some may go to a laboratory, some may go to private sector, and so on. And so we can't keep track of those numbers and whether these folks are staying in STEM or leaving STEM altogether. So, so we just urge that we work on ways to quantify this information better in order to try to help. Yeah.
I actually have a question about the first paper you talked about with culturally relevant communication. So that study seemed to show the effects of communicating just one topic, and you kind of said the conclusion was that both styles are needed. So I was wondering if you guys had thought about if there are different types of concepts might be more effective in one style of communication rather than another. For example, like fundamental knowledge through the more traditional video versus applied like adaptation knowledge, maybe through the conversational techniques.
That is a great question. Yeah, so the videos focus on just one very specific topic, like you noted. So strictly looking at mountain weather, right? And so I will say lots of Hispanic people grew up in Florida, at least like I only say that because I did. I grew up in Miami. And so like I had no idea what mountain weather was before I moved to Colorado, other beyond going to school and learning about it. But yeah, so there might be a signal in there related to the topic and related to how much someone knows about that topic before they watch either one of these videos. And so the questionnaire attempted to extract that information by asking like, how much do you know about this topic and so on and so forth before watching the video, to try to see how much was like learned or how much their responses improved, while also trying to balance keeping the survey to a time frame that wasn't too much of a burden on participants. And so, no, this was just one specific topic, mountain weather. It's possible that different topics might resonate differently or require different type of science communication. And but I think for me, again, it was just the assumptions that we had and the hypothesis that we had were kind of totally wrong, at least on this one very specific study, and surprising. And so we also realized that even though we are Hispanic and Latinx, we have been in the US for a long time, and perhaps we've also been Americanized and our own opinions are have been changed based on our lived experiences. So it's complicated.
Yeah, it sounds really complicated, but either I think it's really cool that you guys are like trying to understand it and starting to do some of that work. So
Yeah, and I will totally 100% credit goes to Anarelli Morales. This was her idea, and she really worked hard on that.
do we have any other questions either here or online? Like I said, you could just unmute yourself if you want to ask a question.
Maria, I had a clarifying question on your PhD students' work. You had a bullet, and I might have missed it, but you had a bullet saying something about persistence, and I'm wondering if you could just clarify that takeaway for me. I think I missed it.
Yeah. I'll also, mention that that is ongoing work. So Jairon is still working on this topic, and essentially, what he did was he wanted to get some sort of baseline to compare the neural network to, right? And say, hey, is this neural network actually giving us value added or skill over some sort of metric, like benchmark metric? And so what he did was he looked at persistence, meaning if you're using persistence, it's like assuming that the weather regime continues to be the same as the day before. And so for weather regimes overall, at least based on CESM and Era 5, we're about 2 weeks or so, with a lot of variation in between. Like there were some extremes that lasted like over 35 days or so. And so the thinking there was, okay, just use persistence as something to compare to. And so that's what he did. And use that as the comparison to see if the convolutional network could perform better than just saying continue the same weather regime. Does this make any sense?
Yes.
It's really confusing to me, the concept of like persistence as a baseline, and I don't love it, I will be honest. But it's something to compare to.
Right, cool, thank you.
And there are likely people on this call, based on the names I see, that would be much more able to explain that eloquently than I can.
Okay, if we don't have any more questions, I think maybe we can just give Maria another round of applause.
And thank you.
Thank you for taking your time and sharing all of this with us. Yeah, so I think we can just conclude a little bit early, and feel free to stick around if you want to keep going with the discussion, but.
Yeah, thank you. I hope my talk was more interesting to you than it was to my dog, who fell asleep.
Oh my gosh, so sad. How's Cumulus liking Maryland?